Hey guys, I'm going to do this very last video for all homework assignments, which I am so excited for. So 10.13 through 10.15, what is the interval of convergence for this power series? So if you're trying to find the interval of convergence of a power series, you need the ratio test. Ratio test will tell you what the interval radius of convergence is, whichever one you need. So the ratio test, if you guys remember, is the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. So let's go ahead and in this very limited space that we have, let's do the limit as n approaches infinity of the absolute value. I'm going to ignore this part right here because I'm using absolute value and the negative terms aren't going to matter. And so I'm going to do x minus 2 n plus 1. So x minus 2 n plus 1, because again I'm finding the nth plus 1 term, so basically just wherever you see n, you're using n plus 1. So we have x minus 2 n plus 1 over n plus 1 instead of n, and then 5 to the n plus 1. And then we're going to divide this by the nth term. Now the nth term is this expression right here. So I'm going to divide by this expression, or I'm going to just multiply by the reciprocal rather than divide. So I'm going to multiply by the reciprocal of this expression. So the reciprocal would be n times by 5 to the n over x minus 2 to the n power. And there we go. So this is the setup for the ratio test. So we've gotten that far, but now we have to simplify the parts. So simplifying isn't too bad. You just have to know how to simplify exponents. You need your exponent properties. So x minus 2 and x minus 2, those can simplify. How do they simplify? Well, because they have the same base of x minus 2 and their quotient, you can subtract the powers. So n plus 1 minus n. Well, that would just be 1. So whenever I simplify this, I'll just have the absolute value of x minus 2 to the first power, because the n's canceled, leaving me with just x minus 2 to the first. And as far as the absolute value signs go, the absolute value signs really only matter for terms that involve using x, since x can be negative, but n, since n is starting with 1 and going to infinity, n plus 1 will always be positive, 5 to the n plus 1 will always be positive, n will be positive, 5 to the n will be positive, so I don't need the absolute value signs around any of these expressions right here. So I'm going to just use the absolute value signs around these ones, which I simplified to be x minus 2. And then I'll just multiply this by whatever I have. Well, the next thing that I can group up and simplify would be the base 5. So I have base 5 n plus 1 in the denominator. I have base 5 to the n. So when that simplifies, it's the same thing, except notice that it's n plus 1 in the denominator rather than n, while for the x minus 2 is the other way around. That just means that we're going to end up with 5 in the denominator. So I'm going to put this part over 5. And then for the rest of it, I kind of just show as being multiplied by everything. So n over n plus 1. So that's everything right here. This is kind of like what won't simplify, but what I'm going to group together. And so what I can simplify, what I can group together and simplify, what I can't. Now notice here that this is going to remain the same as n approaches infinity. As n approaches infinity, it has no effect on x or a constant of 5. As n approaches infinity, is only going to affect this part of my expression right here. And then I just have to evaluate the limit here. And then that just comes from knowing your powers. So the power of the numerator is to the first degree, and same with here, it's just to the first degree. Now that means that at infinity, anything less than our first degree is going to be negligible. It's not really going to matter. And so we're just going to say n over n, or 1 over 1, I guess you can say at that point. So essentially what I'm saying is that the limit as n approaches infinity of this expression is just going to be equal to 1. So this will be the value of my limit. So my limit is going to just be equal to x minus 2 over 5. This is my ratio. So as n approaches infinity, the ratio of the nth plus 1 term over n is equal to the absolute value of x minus 2 over 5. So hence the ratio test, this is my ratio, and we know that if the ratio is less than 1, then the series will converge. And so in this case right here, we're trying to find the interval. So I'm going to multiply by 5 over here. So I'll get the absolute value of x minus 2 is less than 5. By the way, we just found the radius of convergence. The radius of convergence is 5. Now we are looking for the interval. And I'm going to drop the absolute value signs and make it x minus 2. But that also means I'm going to make it a compound inequality and add negative 5 over here. So negative 5 has to be less than x minus 2, has to be less than 5. And then I'm going to solve for x by adding 2. So add 2 and add 2 to these parts right here. And that's how I'm going to get my interval. So I'm going to get negative 3 is less than x, and that's going to be less than 7. And so here's my interval of convergence. And again, you can see, remember that the center is at 2, the radius is 5, which makes sense. So if the center is at 2, if I go 5 to the right, which is what we said to be our radius, so if we're at 2, we go 5 to the right, we're going to get to 7, which is what we have here. If I go 5 to the left, I'm going to end up with negative 3, and there's why I have negative 3 right here. So that kind of just fits with everything that we've confirmed. Center is 2, radius is 5, intervals from negative 3 to 7. Now the part is there's two options that are here, so it's not going to be C, it's not going to be D, so it's all dependent on whether or not I include the endpoint of 7. So how do I know if I'm going to include 7 or not? Or for that matter, how do I know if I'm going to include negative 3? Well, we're not, because there's not an option that we do, but either this is how you would do it if you needed to show. So what we're going to do is we're going to plug in 7 for x right here, and the resulting series we have to run, we have to use our knowledge of series test to see if the resulting series will converge or diverge. So say I plug in 7. Well, this becomes 7 minus 2, which becomes 5 to the n power. So then the resulting series is going to be negative 1 to the n times by 5 to the n over n times by 5 to the n. And then you can see that I can simplify this expression, 5 to the n, 5 to the n, and that's going to be equal to negative 1 to the n over n. And if you guys should have a knowledge of what this series is. This is the harmonic series, the alternating harmonic series. So this is the alternating harmonic series. And we know from class that this series diverges or converges. The alternating converges. Now, so the harmonic series diverges, but the alternating harmonic series converges. So, because this series converges, and this is the series that resulted from us plugging in 7. So that makes sense that this would have to converge at 7, so I'm going to include that. So that's going to be B. So this is a good question. Guaranteed you're probably going to see this on the test. Like, I put money on it that you're going to see it at least once, if not 2 times. You might see it on a multiple choice and on a FRQ, probably. Alright, so for what values of x does the series converge? So again, we're trying to see for what values of x. That's basically asking for the interval. We said for the x values here from negative 3 to 7, it's asking the same question, so we're going to need to use the same test, the ratio test. So let's do the limit as n approaches infinity of the absolute value of the nth plus 1 term. So that's going to be 2x minus 3 to the n plus 1 over n plus 1 factorial, and then times by I'm going to multiply by the reciprocal, so n factorial over 2x minus 3 to the n power. And then let's do some grouping and simplifying exponents. So n plus 1 and n, that's going to result in just the absolute value of 2x minus 3, and then times by, well, n factorial, so we haven't talked much about the factorials. So n factorial over n factorial. So let me kind of go off on a tangent here. So n factorial is equal to n times by 1 less than n times by 1 less than that, so that would be 2 less than n, times by n minus 3, so on and so forth. N plus 1 factorial is equal to n plus 1 times by 1 less than n plus 1, which would be n, times by 1 less than that, which would be n minus 1, times by 1 less than that, which would be n minus 2. So, well, here's the thing. This portion that we have right here is n factorial. So basically what I arrive, if I have n factorial over n plus 1 factorial, that's equal to n factorial over n plus 1 times by n factorial. Well, that's nice because then those would actually cancel. All these factors would cancel with everything from there, leaving me with only n plus 1 in my denominator. So keep that in mind. That's a common simplification technique that you use with ratios and with the ratio test, because if you have n factorial and you're trying to find convergence, you're going to want to use the ratio test. It works really nice. So if you have n factorials and you're trying to find convergence, think ratio test. And so in this case, so n factorial over n plus 1 factorial, that's just going to be times by 1 over n plus 1. And so I've kind of explained before why I keep the absolute value signs here, and why I keep these separated, because as n approaches infinity, that has no effect right here because there's no n. And so the only thing I have to evaluate the limit of is this expression. And the limit as n approaches infinity, well, that's going to make my denominator very large, which is going to make my overall expression go to 0. So that means this doesn't even matter. Everything is just going to be 0. And if the result, so in this case right here, we actually had a ratio. We don't have a ratio. This was a ratio. Whenever the ratio is less than 1, the series will converge. What if the ratio is 0? Well, what that means is that the interval of convergence, so for what values of x, this is the result is that it converges for all real numbers of x. So it's not going to, there's no radius, I guess you can say. Well, the radius, there is a radius. The radius is infinity. So if the results of the limit test of a power series, not of a regular series, of a power series is 0, then the series converges for all real numbers x. Alright, and for 3, we're going to see a third case. So far we've covered 2 cases of the ratio test of power series. So there's the case where there's actually a finite interval. And then the second one is that if it's equal to 0, it converges for all numbers x. And then the third case, well, let's go ahead and see what we get here. So we're trying to find which of the following statements about the power series is true. Well, all of these are talking about an interval of convergence, so let's go ahead and find that. So we'll do the limit as n approaches infinity of the absolute value of the nth plus 1. So that's going to become n plus 1 factorial times by x to the 2n plus 2. Because I'm going to plug in n plus 1 right here, and that's going to multiply by 2, so you distribute the 2, and you get 2n plus 2. And now, in this case, I actually am going to, I know for every example, it always just feels like we're multiplying by the reciprocal, but in this case, I'm actually not going to multiply, well, I am still multiplying by the reciprocal, but because this expression is not a ratio itself, then I'm just going to divide by a sub n. So divide by n factorial and x to the 2n. So no need to do a keep change flip. The reason why we need to multiply by the reciprocal is this is a ratio, and the nth plus 1 term is a ratio, which requires that keep change flip rule, but not in this case because it's not a ratio. All right, so we've talked about n factorials, and so here are the groups. So let's simplify. We get the limit as n approaches infinity of the absolute value 2n plus 2 over 2n. If I subtract those cancel, so I'm just going to be left with x squared. So there we go. And then what is n plus 1 factorial over n factorial? Well, in the previous problem, we did n factorial over n plus 1 factorial. That results in n plus 1, but this was in the denominator. But because n plus 1 factorial is in the numerator and n factorial is in the denominator, this will result in n plus 1. And now let's evaluate the limit. The limit as n approaches infinity, that's going to be infinity. So all of this is just going to be an infinite. So now we come to our third case. What if the limit is infinity? If that's the case, then the only point of convergence is going to be the center. And so the center is at x at 0, and so B is going to be the only point of convergence. So the series converges for x equals 0 only. So the three options are an interval. It's always going to converge for all x, and that's if the limit is 0. And then there's the case where if the limit is equal to infinity, then it only converges at the center. So remember those three cases. All right, for 4. Which of the following are the first 4 non-zero terms of the Maclaurin series for the function g of x defined here? So this is expansion. So first of all, I'm using e to the x. So what is e to the x, the Maclaurin series for e to the x? It's 1 plus x squared, 1 plus x, sorry, plus x squared over 2 factorial, plus x to the third over 3 factorial, plus x to the fourth over 4 factorial, plus so on and so forth. Now I'm just going to start taking this right here and build out a new Maclaurin series, but for this expression. So first of all, let's find what e to the negative x. Let's use this to find what e to the negative x is. So e to the negative x would be 1 minus x, because I'm substituting negative x in, right? And then if I substitute negative x here, well, because it's being squared, it's still going to stay positive, x squared over 2 factorial. And that's going to make this one negative since it's an odd power, so minus x to the third over 3 factorial plus x to the fourth over 4 factorial. So, well, here's e to the negative x. Now I want to multiply that by 1 plus x. So what is 1 plus x times by e to the negative x? Well, that's going to be equal to 1 plus x. I know you guys can't do this, but I'm going to move this up here so that I can actually have some space. So 1 plus x times by e to the negative x. So here I have 1 plus x, and now I'm going to multiply it by e to the negative x, which I started writing out right here. So multiply by 1 minus x plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial, so on and so forth. Now, whenever I multiply these together, I have to distribute that, right? So I'm gonna FOIL this out. And now notice that I don't have to keep foiling. So I'm going to do 1 times by x times by x squared times by x to the third times by x to the fourth. And then I'm going to have to do x times by all of those terms right here. However, I only want the first non-zero terms. So in that case right here, I'm going to keep that in mind. I only need 4 non-zero terms. So 1 times by 1. So that's going to be equal to 1. 1 times by negative x, so minus x. 1 times by x squared times by 2 factorial, so that's just going to be plus x squared over 2 factorial. 1 times by x to the third, so x to the third over 3 factorial. Then minus x to the fourth over 4 factorial. I think I'm good there. I'm going to stop there. I could keep multiplying 1 in, but remember that I'm only going to be collecting the first four non-zero terms. But now I have to multiply x by all of these terms right here. So x times by 1. So plus x, and then x times by negative x, so minus, I'm also going to line these up because these are going to combine. So minus x squared, and then so x times by that, x times 2, so it's going to be plus x to the third over 3 factorial, right? When I multiply it here, x to the third over 2 factorial, sorry, not 3 factorial, over 2 factorial. Man, I'm running out of space again. I need to clear, oh my gosh, I need to select the right thing. Move those up. Move these down a little bit. And then, so I did x times by 1, and I got x. I did x times by negative x, got negative x squared. X here, that's going to be x cubed over 2 factorial. X, that's going to be x to the 4th over 3 factorial. Ooh. Where's my negative signs? Uh-oh. Positive, negative, positive, negative, positive. Did I mess that up before? So negative, positive, that should be negative right there. And then that should be positive right there. And so that's going to be positive. That's going to be negative. That's going to be positive. Okay, and then x here, that's going to be minus x to the 4th over 3 factorial. All right, so I think I'm probably good. Now I just have to combine any like terms. So I have 1, and then I have negative x and x. So those actually cancel. And then I have x squared over 2 minus x squared. That's going to result in negative x squared over 2, right? So minus x squared over 2. And then I have x to the third, so I have negative x to the third over 3 factorial, which is 6, and then plus x to the third over 2 factorial, which is 2, and that's equal to negative x to the third over 6 plus 3 x to the third over 6, which is equal to 2 x to the third over 6, which is equal to x to the third over 3. So plus x to the third over 3. Okay, and then so I have 3 non-zero terms, so 1, 2, and 3. And then for the 4 non-zero terms, so then, well, I actually think I can get my answer right now. So I know it's not going to be 2x because we have it, those canceled. And then we do have 1 minus 1/2 x squared. And then we just got that it's 1/3, not 1/6. So the answer is going to be D. All right, for 5. All right, 5 might feel pretty unintuitive. It honestly just comes through experience. So whenever I take a look at this series, we're going to have to rely upon any known series that we know of. So sine, cosine, e to the x, or 1 over 1 minus x. So what does this look most familiar like? Well, I see 3 factorial, 5 factorial, 7 factorial. So the only expression where I get odd factorials is sine of x. So sine of x is equal to x plus x to the third over 3 factorial. Oh, no, not plus. It's going to be minus. And then plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus ... Now, there obviously is there's some big changes here. So, but I'm going to start with this, and I need to manipulate this expression to match this expression right here. And ideally, what the goal is that I can't necessarily evaluate an infinite sum, but I can evaluate this side right here because I'm familiar with sine of x. And so that's what we want to do. We're going to manipulate both sides to get this right here. Well, first thing that we need to recognize is that we're not using x. Each term is pi halves in place of x. So pi halves, pi halves. So let's do that to the left side. So we're going to have sine of pi halves, and that's going to be equal to pi halves minus pi halves cubed times by 1 over 3 factorial plus pi halves to the 5th times by 1 over 5 factorial minus pi halves to the 7th times by 1 over 7 factorial. So we're getting closer. However, these don't have the same powers. This is 1 less than that, 1 less, that's 1 less right there, and this is just 1, not pi over 2. So what could I multiply each term by in order to get rid of a factor of pi over 2? Well, I can multiply each term by 2 over pi. 2 over pi times by this would be 1. And if I multiply this by 2 over pi, that will decrease that to 2. That will decrease that to 4, and so on and so forth. So multiply everything by 2 over pi, but that would also mean I'm multiplying this by 2 over pi. So 2 over pi times by sine of pi over 2 would be equal to 1 minus pi over 2 squared times by 1 over 3 factorial, and so on and so forth. So now I have the same series, but I also have an expression that it's equivalent to. Now I know how to evaluate this right here, which will help me evaluate this right here. So I know that sine of pi halves is 1, and 1 times by 2 over pi is 2 over pi, which is one of our options right there. Alright, for 6, which of the following Maclaurin series for the function f defined here, which of the following is the Maclaurin series? Alright, so notice here that we're using cosine of x, and cosine of x is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot, so on and so forth. And then, so that's what cosine of x is. So I could substitute all of this right here for that. So I can say that f of x is equal to 1 plus x squared plus cosine of x. So plus 1 minus x squared over 2 factorial, which is 2, plus x to the 4th over 4 factorial. 4 factorial is 4 times by 3. 4 times by 3 is going to be 12 times by 2, so 24. And then so on and so forth. And then I'm just going to combine like terms. So I'm going to get f of x is equal to 2, because we got 1 and 1. And then we have x squared minus x squared over 2, which is going to be plus x squared over 2 plus x to the, plus x to the 4th over, I don't know what I'm writing. Why am I writing so much of that? X squared over 2 plus x to the 4th over 24. Alright, and then we basically have our answer, so it's not going to be C, it's not going to be D, it's going to be A. Okay, and then we've got 7. Oh, looks like I already did number 8 for somebody. Alright, for 7, let f be the function with f of 0 equal to 0 and derivative given here. Which of the following is the Maclaurin series for f? So first of all, let me find the series for f prime. This is the function, but what would be the series? Now, if you guys remember, we have talked about that there is a series for 1 over 1 minus x. And the series is 1 plus x squared plus x to the 3rd plus x to the 4th plus dot dot dot. Yeah, that's what we need. All right, well, that's almost like this, but not quite. So what do I need to change about this to get this? So this part right here, I can rewrite the denominator as 1, or I can rewrite this expression, I'll say, as, I'm just going to do this. So I'll say f prime of x is equal to 1 over 1 minus negative x to the 7th. Okay, well then how do I change this series to fit this expression right here? Well, this is just, I can just substitute negative x over 7th for x in all of these terms right here. So I can say that f prime of x is equal to 1 plus negative x to the 7th, and then plus negative x to the 7th squared, plus negative x to the 7th cubed, plus so on and so forth. And that's going to be equal to, so I'll say f prime of x is equal to 1 minus x to the 7th plus x to the 14th minus x to the 21st plus dot dot dot. All right, so now I actually have something that represents f prime of x, which means I can use that to help me find f of x. So f of x is going to be equal to, what's the antiderivative of 1? That's going to be equal to x. What's the antiderivative of x to the 7th? That's going to be minus x to the 8 over 8, and then plus x to the 15th over 15, minus x to the 22nd over 22. So I think we have an answer here. We should have A. All right, I'm gonna have to pause this video and be right back.